So our project for process control was to make the perfect bullseye. The three of us that worked on it was Alan Black, Tanner Smith, and Justin Ward. So just to start off, we'll start off with a video from a Disney movie that gave us the idea to implement a controller.
Sure.
So we wanted to build a controller that would move just like the guy did for the bullseye. So that one worked for an arrow. We're going to do it for a dartboard. So here's the apparatus. So this shows regulation size dartboard, the height, and the distance to the dartboard. So every time you throw the dartboard at no matter which angle, up, down, left, right, you want to make it so the dartboard can move. So you would hit a perfect bullseye each time. So the controller needed to move the dartboard in the Z directions, which is the left and right directions, and it needed to move it up and down, which is the Y directions. So what the controller will do is it'll read in what's the error for where the arrow is and where the dartboard is, and then move to minimize that error and make sure that when the dart hits the dartboard, it's right at the bullseye. So this is actually implemented a while back by Mark Rober, and so you can see a video of his controller working. So one thing you'll notice there, he got it to work perfectly. And one thing that was really, really challenging is just how fast the dartboard has to move, because it only takes half a second for the dart to reach the dartboard. So the controller's got to move really quickly so that it hits the right of the bullseye. Because we were unable to build the actual physical apparatus, we just wanted to simulate it. So we simulated the motion of a dart, which we just used force balances on the dart. So these three differential equations, which is in the X, Z, and Y positions, the differential equation just will know the position of the dart at any moment. So this is dependent on the velocity of any type of wind, which is going to be our disturbances. It'll also very dependent on K, which is the friction coefficient. So just some background to some other things we'll be talking about is theta, which is the angle, the up and down angle of release, and phi, which is the left and right angle of release.
So when we actually implemented this, we used a proportional integral controller. The derivative term we found was unnecessary. And we found that for values less than 0.93, the gain was stable. And for values greater than 0.006 seconds, the time constant returned a stable result. You can see on the right here an unstable result. It took about half a second for the dart to reach the dartboard, but the dartboard would have been going crazy at the end there with that unstable result. We decided to go for a stable controller of 0.925 for the gain and 0.006 seconds for the time constant. As you can see, in both the Y and the Z directions, this led to a stable controller.
So if you look at this little GIF here on the right of our simulator, the dartboard tracks every movement of the dart, and that dart is represented by a pink arrow. They're centered up on the bullseye. So just like Justin was mentioning, the physical constraints of moving a dartboard fast enough at such a short distance to account for the dart is really difficult. So we just restricted the movement to a 1 foot by 1 foot box. Here on the left are the inputs placed into our simulator. So velocity of the dart thrown, the two angles of release, wind velocity, and the two angles of wind velocity that affect the dart as our disturbance. Here's a different example without that disturbance. The angle of release is a little weak, so it was outside of our box, but still the dartboard was moving in the right direction. Another example here, dartboard tracked the movement, captures that dart, perfect bullseye. Here we just wanted to see what would happen if we had no release, so basically just throwing the dart at a flat angle, no wind resistance. It just falls straight down like you would expect. Our last example here, notice how it tracks it as it goes really high because that release angle is really high, and then quickly adjusts for it to fall and captures that perfect bullseye.
In the future, we'd like to include hardware with this project. We only did simulation, and so hardware that would be included includes an imaging system, retroreflectors, the kind of thing you would need to know where the dart is at any point in time. as well as controllers to move the dartboard. And as you can see here, there are 6 motors that are used to control Mark Rober's dartboard in that YouTube video we showed earlier. And that is our presentation. Thank you very much.